go ahead.
Hey, everybody. Hope all of you are having an amazing time here at reInvent. I certainly am. Been here in 2016, 2017 in the audience, and this year coming and presenting here, super excited about it. My name is Shriman Sudraraju. I'm the lead digital solutions architect. I'm from the London office in the UK, and I'll be joined by Santiago from AWS.
Hi, everyone. Santiago Freitas. I'm a principal solutions architect with AWS, supporting HSBC. Delighted to be here with Srimanta and sharing some of the lessons learned that we learned while building this platform to enable HSBC to better communicate with their customers.
So, what's the objective? The objective is to provide a reference architecture to actually build a distributed system leveraging serverless technologies, and to share some of the lessons learned that we have been through, so you don't fall in the same pitfalls, but instead you make new ones, come here and present in the next reInvent. Yeah? Let's have a quick overview of the agenda. I'll give a quick overview on what HSBC is, and we look at the business problem we are trying to solve, and then we look in the solution on how we are trying to solve the business problem. And then as part of that, the design considerations and the lessons learned, and then have a quick look on the monitoring and scaling at scale, and then some of the key takeaways when you design such a solution. So HSBC, right? HSBC is one of the world's leading international banks. It's the 7th largest in terms of assets and market capitalization. It's primarily split in 4 business units: private banking, commercial banking, investment banking, and retail banking. Established in March 1865 and been in operation for 150 years since. So what does it actually mean, the size of the bank, right? It has its own complex problems. We have multiple source systems and legacy systems. It's very similar to a lot of people from different countries. They speak different languages, right? You can't talk to each other. Our legacy systems are like that. So it has a lot of problems and geographically dispersed systems as well. Highly regulated industry. The last I know that we were interfacing with about 500 regulators. That's massive, right? And today's world is all about digital transformation and more digital, which means there's immense pressure on our source systems and backend systems. So how do we actually come out of that to give a better digital experience for people for tomorrow's world, right? So what we have done is to solve the problem. Initially, we have created an organization within HSBC called HSBC Digital a couple of years ago, and with a view to simplify technology, provide better innovation, and deliver better customer experiences. And as part of our HSBC Digital, right, we have embraced AWS as a key partner in delivering our strategies. What does it actually give us? It gives us mainframe abstraction, and we can deliver faster route to market, drive better personalization. It gives us increased agility, security, performance, and all the yada yada of clouds, right? So in HSBC Digital, we embraced AWS. Okay? All of this is well and good, but what's the business problem that we are trying to solve, right? So traditionally, within a banking industry, if you see anyone who's actually using their apps, they check their accounts once or twice a week. You check it, you're OK. Some people, lazy enough, they check it once a month. Some people don't even care, right? Yeah, whatever's happening, right? Today's generation, if you see, they keep checking their accounts, blah, 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 right? And it's a constant habit. And it's not only with the banking world. I'm pretty sure, look, so many of you have already been checking your mobile phones, right? And we're not even 5 minutes into the presentation. It's you want to have your fingertips at your, information at your fingertips, right? What does that actually lead to? Let me actually alleviate with an example. I'm a dad of 2, and I'm driving on a holiday with my 2 kids at the back, okay? A mile into the holiday, they start saying, Papa, are we there yet? Are we there yet? Right? Not even a mile. Can you imagine that, right? Nothing's actually changed. They keep constantly nagging you, are we there yet? Are we there yet? Right? I am the mainframe. My kids are digital consumers. Nothing's changed. There's the same pressure, right? So eventually, it's a big business problem for every finance industry, right? lots and lots of digital customers are coming and hammering you, nothing you can do. So from HSBC Digital, what we said is, OK, let's turn it around. What do? We said, hang on, let's inform the customers in real time, rather than them coming to us for information, right? What does this give you? It gives us two things. One, it drives better digital experiences. And two, it actually reduces our loads on the mainframes and the backend systems. OK? So I'll go into the solution now. So what is actually what we did with regards to solution? OK? So if you can see the screens, this is a very animated screen, so you can follow the screens. First of all, we actually created microservices architecture completely. And the first step that we took was, what does a customer actually need? Right? We need to give them customer preferences. So as part of that, we built a simple customer preferences solution, which gathers what the customer wants in terms of consent, preferences, what they want to be notified on. I'll walk you through a simple use case, a real-time credit notification. Right? Something comes into your account. You want to be notified in real time. Let's take that use case. So as part of the use case, in your preferences, you go and say, oh, I want to be notified. You say yes or no. And then do you want push notifications, yes or no? And then we provide a threshold. Oh, I don't want to be notified for any petty change. Right? I want to be notified for anything over $100 or something. But if you set it to 0, you get notified for everything. Let's say Santiago is actually a customer, and he opens his app, and he sets the preferences. OK? All done, sorted out. And then he's walking along the strip, and then withdraws 500 pounds from the cash machine. OK? So that record goes into the mainframe. From mainframe, what we do is we extract the data in real time onto our on-prem Kafka clusters. OK? From on-prem Kafka clusters, we use Apache NiFi to move it to the cloud. What is NiFi? Apache NiFi is nothing but a simple software tool. It's a data workflow tool that moves data from point A to point B. And Kafka and NiFi are part of our Hortonworks on-prem data suite of products. So once the data is picked up by NiFi, it actually moves to a first microservice called the mapper service. Right? What happens in the mapper service is that it does data transformation, data minimization, and all of the data cleansing. Because the mainframe format is actually EBCDIC, and it's an Avro format. Avro is a data type of format. Right? But for digital, we need ASCII and JSON. Right? So through the ranks, it's actually converted through JSON ASCII. Once it reaches the mapper service then actually converts all of the source data into a proper data format and sends it to a data service. The data service is a combination of Aurora and DynamoDB, and we provide data as a service to the rest of the digital platform. Once the data goes and lands in the data service, then onwards, it's an event-driven architecture within our platform. So the data service then emits root events. As in this case, we withdrew some money from the cash machine. That record has now traversed to Kafka, NiFi, onto Mapper service, and now sitting in the data service. The data service then ejects a base a root event called credit event. Once it injects a credit event, then we have built an event engine. The event engine picks up the credit event, checks who it is for, and checks, has the customer actually signed up to this notification? Yes, no. And all of that. Checks his preferences and checks everything else. And the event engine then decides, oh, yes, this customer actually needs to be sent a notification. Then the event engine then takes up, prepares a full-fledged and in-app message, a rich in-app message, and sends it to a message service for it to be consumed later. And then also tells message service whether a push notification should be sent or not. Once the message service has actually formatted the message, rich message, it then notifies the notification service saying, hey, send a push notification to the customer. Okay? So the notification service sends a push. So you're all somewhere outside, then you get a push notification service on your phone. You actually swipe on the push notification, and then that mobile app authenticates and goes to the message service, and then gets the rich in-app message in your mobile. So we are providing a much more digitally rich experience. Many people have actually asked me, hey, hang on, a lot of people do this. Yes, but they do it through SMS and through other technologies. Here, you're driving your own notifications. So there's a big difference. Each of these services, if you see, is actually a microservice engulfed in its own. No microservice can talk to each other than through API gateways and all of that, which we dig a little deeper into that. And all of the microservices have some common services and dead letter queues, right? I'm going to pause here for 2 minutes, or 2 seconds, sorry, because I see a lot of paparazzi. So fire away. Right. Now let me focus your attention on the color of the arrows, right? Because when you're actually designing your systems for data flow, this is very important. If you see the red arrows, they're all our on-prem traffic, which is BAU standard, right? You see the white line traffic? That is from HSBC to AWS. So that is one pattern of communication. And then if you see the purple arrows, that's within your AWS services, that's pattern number 2. But the purple arrows don't go out to the internet. It's still within the box. And pattern number 3 is the green arrows, wherein from HSBC, it goes to the internet, to the devices, or any other integration third-party providers, okay? Which we'll talk about more detail later. So what are the design considerations and lessons learned? As the saying goes, the devil is in the details, right? Now, Santiago will go through a power-packed crash course on Lambda and Kinesis and their integration patterns.
Thanks, Srimanta. So as you saw on the solution, on the architecture diagram, Kinesis is heavily used on this architecture. And the reason is that it enables a service-to-service communication, a loosely coupled, event-driven way. Whenever I say Kinesis, whenever we say Kinesis on this presentation, we are really referring to Amazon Kinesis data stream. It's a pretty long name, so we're just going to say Kinesis. You know we are referring to specifically to Kinesis data stream. So some of the key concepts that are relevant for, in particular, the integration between Kinesis and Lambda is that in Kinesis data streams, where the data is actually stored is actually on a shard. So a shard is the base unit of throughput. It effectively contains an ordered sequence of records arranged by the arrival time. So the other key concept or terminology is stream. So when we refer to a Kinesis stream, it's really a logical grouping of shards. So when you actually configure Kinesis data streams into the console or through the API, you create a stream, you have to define the number of shards, which is where your data is actually stored. The other important concept here, it's a partition key. So a partition key, which is imposed by the data producer, is actually an identifier that is used by the service, by Kinesis data stream, to route your data records into shards. So the important part here is that data with the same partition key is stored into the same shard. So that you see why that becomes relevant when Srimanta is explaining the implementation at HSBC. The data producer, it's the systems that are sending the records, that's producing the data itself. They are responsible for tagging the data records with the correct partition key, which is then used into the system to route the records into the associated shard. The data records itself is the unit of data. It's made of a sequence number, the partition key, and the actual data blob itself. And the consumers is what's reading data off the stream and then processing the data. So in the case of this architecture, Lambda is predominantly the consumer that's utilized. So let's dive a little bit deeper into the integration between Kinesis data streams and Lambda. First, from a scaling behavior point of view. So the first point here, what it's shown into the diagram, is that for each shard into your Kinesis streams, the Lambda service, when you configure Lambda using Kinesis data stream as the event source, what's actually happening is that for each of the shards that you have into your stream, the Lambda service automatically creates, in a one-to-one mapping, a Lambda container, so a Lambda execution environment for your function. So what's important to note here is that the number of Kinesis streams shards is the unit of concurrence for your Lambda functions that are reading, that are configured to use Kinesis streams as the event source. So regardless of the number of messages or records that's put on the stream, that's not going to trigger more Lambda concurrent execution. It's actually the number of shards defined on the stream that dictates how many Lambda concurrent you're going to have concurrently executing. So as an example here, if you create a stream with 10 shards, you're going to have 10 containers effectively executing. The other point that's important to understand into this integration is that the first in, first out behavior is on a per shard basis. So as the diagram is showing, what you have is each one of the Lambda execution environments, it's only reading from one specific shard. That ensures that from that shard point of view, the records are processed in a first in, first out behavior. First in, first out manner. The other point that is relevant to understand into this integration is that, as you may know, a Lambda function, when you trigger a Lambda execution environment, a Lambda container, if it's not triggered, if it's not processing, after a period of time, that container may go cold, may be terminated. So if you want your system, in this case, to have a consistent latency, it's important that when you are sending data into the stream, that you are evenly distributing how the data is actually arriving to the stream so that you have a continuous flow of records into all of the shards, which means that all of your Lambda concurrent execution environments are continuously hot, are continuously processing data. So that's one thing that you need to consider, and Srimanta will explain how in the case of HSBC, what was the strategy used there in terms of implementing the partition key to ensure that that behavior is executed. The other point that is relevant to dive a little bit deeper when thinking about the integration between Lambda and Kinesis streams is that when you set up your Lambda function to use a Kinesis stream as the event source, what's happening is that that Lambda function basically subscribes to that specific stream and start pulling records off the stream. One of the most important, one of the configuration parameters that you have to choose is the batch size. So how many records at any given, at each interaction, the Lambda service is going to read and pull from the stream. One thing that is somewhat tempting to perhaps to do is to set that batch size to just 1. Because in that way, as Srimanta will explain the HSBC implementation, you could potentially avoid some of the complications of this integration. Particularly, you could potentially avoid having to build that letter queue. But it's important to realize from the experience we had that if you choose your batch size to be just 1, actually the overall throughput of the system goes down. It's badly impacted because there is just too much overhead. So it's important to set a much higher batch size, but that leads to an interesting situation, which is when your Lambda function read a particular batch size from the Kinesis streams, start processing that, all of the records. It's not a matter of if, it's a matter of when you're going to run into a situation where the Lambda function may fail or may try to connect to the remote endpoint, and for whatever reason, maybe it's a network failure, it's not able to connect to. So what you run into a situation here is that if for whatever reason that Lambda execution environment cannot process successfully the batch of records, it actually goes into what's known as a blocking mode, which means that it continuously tries to process the same batch of records until that particular batch of records actually expires out of the Kinesis stream. And by default, it takes 24 hours for a particular records to expire and get out, be purged off the stream. What it means that if you don't consider that, if you don't take that into your design considerations, what could happen is that a particular malformed record, for example, that for whatever reason your Lambda code has not been coded to handle, could actually cause that particular shard to go into blocking mode. And then your Lambda function, basically you're just going to be accumulating more and more records instead of, processing that. So you need to make a design choice on how to handle that scenario. Srimanta will explain what we did in the case of HSBC, which is effectively to create a dead letter queue so that the shard doesn't go blocking. And effectively, even in a failure scenario, we can continue to process a message. Today, we Amazon AWS, we don't offer a dead letter queue by default when you have the integration between, when you configure the integration between Lambda and Kinesis. But we'll go, and Srimanta will go into details on how we architect around that at HSBC. So, Srimanta?
Thanks, Santiago. Before we get into the actual DLQ mechanism, there's an important design concept that I want to walk you through, because that is what ties the entire platform together, and that's the DNA of the platform. So as I said, in the mainframes, right, when a record is emitted, what we do is we actually take the record and move it through Kafka, right? When the payload comes, what we do is we generate a repeatable, unique correlation ID at the source and tag it along with the payload. What does a repeatable, unique ID mean? Hang on, it's unique, and you're saying repeatable. One of the biggest problems that we faced is that when we were testing, we just replayed the same records, and because we generated a new unique ID, we ended up with 2 records, same records, but different IDs. So we started processing, hey, hang on, they're the same. So you need to come up with a mechanism so that if the record is replayed, you generate the same ID again, so which means even if it's come through, it comes as a duplicate, so you know that, okay? Then from Kafka, again, it goes through to NiFi. And at this point, as Santiago said, right, you guys need to be very careful that you set the partition key properly, because you write to the stream, but the producer is the one that determines the partition key that the shard has to go through. Kinesis won't decide for itself, okay? So what does it mean? Let's take a simple example, account numbers, okay? So you say account number 0 can go into shard 0, account number 1 goes into shard 1, and similarly, account number 9 goes to shard 9. There's a problem there. Imagine all of your customers are like, say, from some particular generation that they like only the number 8, so which means your shard 8 is stuffed up, right? 1 to 7 and 9 are empty. So you need to work out a pattern that the volume is distributed across the shards, so you have uniform processing through, okay? So here, the NiFi puts the record into Kinesis stream using the ID that we generate as a partition key, which gives some kind of a load distribution between the shards, okay? Then the Lambda picks it up and then processes it. The distinct advantage of this UUID is operations. Imagine someone says, hey, I have a problem, and we tie the transaction, and what time? Once we find the UUID, we can trace it back all the way to the source system because it's the same UUID going through. And as part of that, we can actually tell which Kinesis stream it has gone through, which Lambda has been picked up, which microservice has processed that, and all of that, okay? So it's effectively gives you an end-to-end lineage also to track a transaction through and through. It's effectively you're finding a needle in a haystack. For operationally, they'll come and love you guys if you do this. So now let's go back to what Santiago was saying about the DLQ, right? Because there's no existing DLQ out of the box. How we did it at HSBC, okay? So as Santiago was saying, let me actually explain a simple analogy, right? You know the freeways? So once you enter a freeway, you're stuck in that freeway. You cannot change lanes, okay? The freeway is a stream. The lanes is the number of shards. And say you have a freeway with 10 lanes, so there's 10 shards in the lane, correct? At the end of that is something actually that is taking away the cars. If a lane is blocked, you're blocked. Other lanes go through. So you need to be very careful in how you design a system so that you implement an amazing DLQ mechanism by which you remove the records or problematic records, so all information still records are actually processed through, okay? Here, based on our performance tests and all that, our current shard size is 20, and our batch size is 500. So the first Lambda, the Lambda container pulls from Kinesis saying, give me the records. 500 records are in the Lambda's memory, and it starts processing. That's how we actually do at most once. What it does is that When the Lambda starts processing successfully one record, once it's successfully processed, it writes to the next system, which is in our scenario, Kinesis queue, and then writes to a DynamoDB state table saying, I've acknowledged and I've processed this UUID, okay? Then it goes to second record and so on and so forth. Let's say that at 100th record, it basically encountered a problem, okay? It cannot process. We have configured it to retry 3 times. And once it fails, what it does is it removes the record, writes it to SNS, then the topic is actually going to SNS, and it stays there, okay? Which means we have removed the problematic record from the batch size of 500, and then start processing it through again. And as you're processing it through, we keep writing, updating the state table. But if you see the 51st problem record, it didn't actually finish processing, so it does not write into the state table. So effectively, we know that that's actually not processed. So we do at most once. Now let's consider the scenario where the Lambda container itself is gone, which means it's actually processed 50 records, and the other 450 in the memory is just gone. When the Lambda container boots up again and goes to Kinesis and says, give me 500 records, Kinesis will give the same batch because Lambda hasn't acknowledged that entire batch. But this time what Lambda does is, when the record comes through, it actually checks with the state table. Have I actually processed this record? Because it's actually updated the state table, it will not process the record and just dump that record. So at this point, say first 50 records were processed, it's going to dump that, and then 51st record, I haven't processed it. There's no entry in the state table, so it starts processing that. So it goes through the entire record. Once the batch size is done, then it does that. And eventually what we do is, in the SQS, we look at all the problem records, we study it, we identify the problems, update our Lambda functions, and then so in future what happens is Lambda functions automatically know how to deal with our records. Over time, right, the SQS will be smaller and smaller and smaller because we know the patterns of problems that happen. So what are the lessons learned, right? Increasing the number of shards does not necessarily result in better performance. Initially, we set the shard size as 2,000 and batch size as 1, right? Amazon support engineers came and said, they were like, they were looking at it in craze, like, guys, what are you doing? And I said, why not? I mean, you haven't set a limit, so I'm going to set it, right? What we realized is that the performance was even more bad. The I/O performance of the container writing to Kinesis back and forth and then writing is detrimental. So instead, then we started working with them and did some tuning, and then we realized that for us, for 20 shards and 500 batch size was pretty good, so work it out, right? Consider the impact of language on the VPC use, right? On Monday, there was another session at reInvent where one of the product managers of Lambda actually gave a brilliant session on what actually happens on the cold boots, right, and how Java actually does that. So it downloads the code, then boots the runtime, and then runs it and all that. So within Java, when you do within the VPC, there's certain cold time for ENI reuse, right? So you need to consider the language on how you're going to do that versus Node versus Python, because different languages have different boot times. But Java, once booted, we found that is the fastest, okay? And to alleviate the problem of that cold starts, you can always pre-warm your Lambdas so you can achieve your designed SLAs. And one important thing is the size of the Lambda. The size of the container is, you can set it up to max of 3 GB. That does not necessarily mean that basically it's the fastest and the most performant, right? Through testing, we realized through ENI reuse, we found 1 GB to be the optimum size, which means we reuse ENIs, so then we actually reduce the boot time problems, okay? And on all of this, if you see, go back to the architecture slide, we actually built microservices. Now, Santiago will walk you through on some of the security considerations and how we have built literally a private cloud within a public cloud.
So let me go through some of the challenge and how we address it. Particularly here in this part of the architecture, one of the requirements that we had from HSBC was how could we provide internet access to some of the functions Lambda functions that need but in a highly controlled way. As you probably know, you can run your Lambda function outside of VPC, or you can choose to attach your Lambda functions to VPCs. In the case of HSBC, all of their Lambda functions are attached to a VPC. And there's a number of reasons for that. One of the reasons is that allows them to set up a security group, particularly the egress rule, so that allows to controls what those Lambda functions can connect to, but also allows them to look at VPC flow logs, for example. So our premise here, our architecture, all of the Lambda functions that we're talking about, they are attached to a VPC. And then that becomes the question, which is, okay, some of those Lambda functions, they may need to connect to the outside world, specifically to public reachable endpoints. In this case, that notification services, a notification microservice actually needs to talk to the outside world to communicate with the provider of push notifications. So what we came up with was with an architecture that we believe allows that, but provides that external access in a highly controlled way. So what we did is, if you look here on the right-hand side, we created a second VPC. That VPC is the only VPC that has an internet gateway attached to that. On that VPC, the HSBC security team, so separation of concerns here. So the HSBC security team created and managed basically a fleet of proxy servers where they control the domains. They have full controls and configure the domains to which those proxy servers allow connection to the outside world. And what HSBC has done by leveraging AWS VPC endpoints is they effectively encapsulate that fleet of proxy servers into a VPC endpoint service. So that VPC, those proxy servers encapsulated on a VPC endpoint service is then exposed into the VPC in the middle, or VPC on the left, which is the application VPC, if you like. That is the VPC where all of the actual work, all of the Lambda functions actually attach to. So in that way, the only network path that those Lambda functions running on the network's notification service VPC have to go to the internet is by connecting to that VPC endpoint that is locally created on the notification service VPC, and that is effectively encapsulating a set of proxy servers that are owned and managed by HSBC security. So a few advantages of that architecture or problems that it addresses. The first thing is that it limits the blast radius. So if for whatever reason, and clearly HSBC has several checks and balances to ensure that this doesn't happen, but in the unlikely, extremely unlikely event that any bad code would land into those Lambda functions that is attempting to communicate to an outside domain that's not approved by HSBC, this architecture will prevent that problem. Because on the Lambda function, if it tries to initiate the connection to a non-approved destination, guess what? It's going to be blocked by the proxy servers. That's going to be logged, and then it's going to trigger an investigation. The other problem that we had to solve from a network architecture point of view, and I highly encourage you guys to think about this problem early on, because otherwise, if you are testing, playing with Lambda, specifically not talking about Lambda attached to a VPC. So if you're playing, testing Lambda attached to a VPC at small scale, later on when you try to scale and run into production, particularly if your production happens to be tens of thousands of concurrent executions, you may run into some problems, and that may cause you to have to retrofit and redesign your VPC, which is not a good thing. So what we encourage you to think about this problem early on. So what we did here is, as you see, we have this platform VPC. That is a VPC where all of the work actually happens. That's where all of the Lambda functions are actually attached to. And as Srimanta referred to, here we're talking about thousands and tens of thousands of concurrent executions. And what it means from a network point of view is that those Lambda functions will consume, when they attach to a VPC, thousands or even tens of thousands of IP addresses. So when working with the HSBC, we went back to the HSBC networking team and said, hey, could you give me IP range, a CIDR block for me to put on that VPC? But by the way, we need about 15,000 IP addresses. They highly encourage us to look a little bit deeper and say, well, how can you actually solve that in another way? That's why we came up with that architecture. So what we do here is somewhat similar to that other pattern that you saw on the previous slide. We created a second VPC. That VPC also has a set of proxy servers. Those proxy servers on that second VPC on the left-hand side, it's the VPC that has a direct connect attached to it, so has connectivity back to on-premise. It's a VPC with a much smaller CIDR range, so, and it's an IP range that is reachable, I should say, from the HSBC on-premise network, but also from that VPC, you can reach back to on-premise. And what we did is, again, using VPC endpoints, encapsulated those proxies into a VPC endpoint service, exposed that into the platform VPC, which is where all of the work is actually happening. Now, the Lambda functions sitting on the platform VPC, if they need to connect back to on-premise, they will talk to that local VPC endpoint that dance to the proxies on the left, which are the ones that actually have the connectivity back to on-premise. So what that architecture allowed us to achieve is that on that platform VPC, HSBC could had a chance to configure that with a very large CIDR range, CIDR block /16, 65,000 IP addresses. It's using an IP range that is independent from the on-premise range. So the key value of this architecture is on that platform VPC, we can scale unlimited, really. IP address space, IP address is no longer a constraint. So, can scale for as much as we need to. So, and we did that without exhausting, without consuming a large number of IP addresses from the on-premise range. So, some of the lessons learned from a networking architecture point of view, we felt that having a resource with a good knowledge of networking to the cross-functional team that was building this platform saved time, allowed us to collaborate closely and build this architecture. As we spoke on the second point, consider isolating your functions within a VPC that has a very large CIDR, because although Lambda, amazing in terms of scaling dynamically, if for whatever reason, if you configure your Lambda function to attach to a VPC, and when the service trying to create a container, an execution environment, cannot receive an IP address from the VPC service, actually your Lambda function can't scale. So running out of IP addresses in your VPC will have a direct impact on the ability of your Lambda functions to scale. Attaching your function to a VPC, from a security point of view, there is tremendous value. The use of security groups, flow logs, and ability to tightly control what does that function can actually communicate to. So let me now pass to Srimanta to dive a little bit deeper in other aspects of the system, which is around monitoring and alerting.
So in traditional monitoring and alerting, there are three things that usually on-prem server guys actually monitor, right? Amount of RAM, CPU, and disk usage. Based on that, you do scaling and all of that. Imagine you turning up, hey, we're going serverless, none of those matter anymore, right? It's a different world. So what do you actually do to monitor, right? Instead of the traditional, what are you monitoring? You go into different, it's a mind shift change. What are you monitoring? At HSBC here, we are monitoring throughput, latency, errors, and system health, a lot of other metrics, specifically our end-to-end latency, because you got to tell that to the business, right? So the challenges in calculating an end-to-end latency is that there's Kinesis Lambda. In individual, you can't track it through. If you remember, I told you guys that the correlation ID, that's what you do here. At the source, when the correlation ID is generated, there's a timestamp. At the end, it is timestamped again, and the difference gives you the end-to-end latency. It does not matter how many points it has gone through, but that's the end-to-end latency, okay? So our Lambdas actually write custom metrics into CloudWatch, and we have out-of-the-box metrics for AWS services. They're all collated in CloudWatch. And then from there, it's actually polled through Datadog, our monitoring solution. And then from there, we produce our dashboards, and then we do our alerting solution. As part of that, within Lambdas, we write certain tags into CloudWatch, so you can actually accumulate all your graphs through the tags. And all of our alerts and logs and monitors are all actually set up hierarchically. So we have a platform-level dashboards. You click on the dashboard, then you can go to the microservices level. As in the microservices, the previous slide I showed you the microservices architecture, as in the data service, the mapper service, message service, so. So then you go into the microservices, and then it goes to the component level. So you can actually dig both, and everything is aggregated upwards, okay? So our dashboards are actually automatically configured, as in configured and then deployed through code. So nothing is actually built in the production system. That gives us a distinct advantage that it's configuration-driven. You configure it in dev, and you promote it through your environments, which means it's deployed actually alongside the code. So they are deployed together. What this gives us a benefit is that we can quickly change and use it for different environments because it's all configuration-based. It's all logically grouped, right? And one interesting thing that we actually enable is anomaly detection. If I can get your focus on the graph, on the middle right-hand side graph, you see the gray area, right? Based on the volumes, that is our actual pattern of usage, okay? And today's pattern is the red line, which means, hey, we're well within our operational limit, so there's no problem at all, right? And if you focus on the left-hand side middle graph, I don't know if you can see it clearly, but the gray area, but if you can see the gray area, that's based on usage. You see the blue line, right? That's outside of our regular usage patterns. So then, which means that we know that that's an anomaly. Something is happening. So we automatically trigger an alert and write it to SNS, which sends an email to our production operations support, and they have a look as to what is happening. So you guys need to be proactive because it's serverless, so you need to be aware of what is happening. As a simple example, say the Lambda to Kinesis connection is broken, or something happens, right? Suddenly you start your line going, which means then they can go in and see what the problem is and fix it straight up. So what are the key takeaways that this entire session we have been talking about, right? We walked through a lot of business problems, solution, and all of that, right? Follow the principle of extract once and reuse multiple times because you don't want to be hammering the mainframes, right? Extract the data from mainframes, process it elsewhere. Do whatever you need to do. Think about the are we there yet scenario, okay? Have it separately, keep processing it separately, okay? Generating a repeatable correlation ID, right? This gives you distinct advantage, as in you can do end-to-end lineage, you can do data lineage, operations, support, and your DLQ mechanism as well, okay? Then perform load tests and identify your choke points. We did a performance test, as in initially, as I said, we did 1,000 shards and one batch size. We performed really poorly, even than a normal dev system, right? So you need to perform lots of load tests to see where your choke points are. Know the AWS soft limits and hard limits, right? If, for example, in your documentation, it says the number of shards is 500 as an example, find out if it's a soft limit or a hard limit. If it's a soft limit, you can change it at your account level, but if it's a hard limit, you can't go beyond that. So play around with your soft limits. Don't play around with your hard limits because you will end towards your end of the system. You can't scale upwards. Plan your network architecture so that you isolate everything within microservices, and effectively you're building your own private cloud within a public cloud, so there's no outside interference or anything, and you're locked down. And effectively, it gives you amazing scaling parameters, like how Santiago explained, so you can scale thousands of Lambdas without affecting your on-prem IPs as well. And the most important thing that we spent the most was how did we actually integrate our on-prem logging to our cloud logging. We went away in a silo and started building a cloud monitoring solution. And then we came to on-prem saying, hey, you got to monitor this. They said, It's not working, right? So then we had to integrate in such a way that all of the cloud logging and statistics, we had to stream it on-prem. So even they got a view of the dashboard. Of course, they go to cloud to actually fix problems, but then you have to have a unified operating model so that they can actually look at both. So with that, I thank you very much for the session. And it's been brilliant presenting this platform, and hope you got some value out of this session. And if you can read the app.